Okay, GAN is a short word of generative adversarial network. So generative means we now a little bit familiar with generative, right? Generative means it's a little bit different from discriminative, right? We are interested in distribution of data instead of distribution of label. That means generative. Adversarial means fighting each other. Some things are fighting each other. They have different, almost opposite objective function. So that something is fighting each other. That means adversarial. Something is not in good relationship. Something is some kind of bad relationship between each other. Network, your network. So we make a generative model, but different. A little bit interesting thing is adversarial. Adversarial is included in its name, so that we can think that something is fighting each other inside of GAN, right? Because we have adversarial in its name. So two modules are trained in adversarial way. Two modules are fighting each other when training. There are two modules, generator and discriminator. Generator is used for both training and testing. Discriminator is only used for training. And there's no encoder. As you can see, this shows just a simple pipeline of GAN. There's no encoder. VAE, we have, when training VAE, we have this input image X, and then we have encoder, right? VAE, we have encoder, but GAN, we do not have encoder. We always start with the random noise from normal Gaussian distribution. Normal Gaussian distribution. And the generator, it acts like decoder in VAE. It generates image. And there's a discriminator, which we'll learn later. But these are some difference and characteristics of GAN. Two modules are trained in adversarial way. They are fighting each other. They have different objective function. There are two modules. Generator, it is used for both training and testing. Discriminator only used for training. The good points are it gives sharp images. VAE is suffer from blurry images, right? Latent space is not very expressive. But GAN images are very sharp and quality is good. And fast inference, as I introduced, in the test time, in the inference stage, we get rid of discriminator. And we only use generator, right? And then we only have a single feed-forward pass. That means generation is fast, but training is very unstable, unfortunately, because we have the two modules are fighting each other. They are trained adversarial way, so that training is very unstable, and then because the primary reason is that supervision's information is too sparse. So we will learn, but these are the only supervision that typical GANs are trained with. Just a binary signal, real and fake, good or bad. Let's imagine you do something, you do some homework, and your teacher says it's good, it's bad, without any detailed guidance. Then that makes your progress quite slow, right? That is GAN. Supervision signal is very less informative, just good or bad, that's all, without any detailed guidance. In case of VAE, we have reconstruction loss, right? Reconstruction loss is very informative. We have explicit target, so that reconstruction loss is very helpful to train some system. It's very informative. But GAN, the supervision signal is only good or bad, binary. So that supervision signal is too sparse, and then that results in mode collapse, which we'll learn later. So these are some characteristics of GAN. As I introduced, there are two modules, the generator and discriminator. Generator takes a vector of random noise as input and generate an image. And discriminator takes an image, classify whether it is real or fake. This figure shows, right? Generator takes random noise and then it generates some image. Discriminator tries to classify whether this image is real image or fake image. So generator, one of the most pioneering work in GAN is DC GAN. As you can see, from random noise vector, it does some convolution, fractionally stride the convolution layer. So to upsample vector to some image space, this fractional stride grows the size of image from layer to layer. And final layer has 3 channels for RGB, right? Because the final layer should have a image representation, right? So from randomly sampled vector, this generator in DC GAN tries to upsample the vector to image space, whose channel size is 3 for RGB channel. This generator, and it looks like a decoder of VAE, right? Decoder of VAE also takes randomly sample vector and upsample it or do something, and then finally output some image, right? So the generator of GAN and decoder in VAE have similar roles. And discriminator, so we can, this is not strictly tied with the convolution neural network. We can use any architecture, but at that time, typically people use CNN, and they simply takes, as you can see, takes an image and classify whether it is real or fake. Real means not generated images from data set. Let's say we have a huge amount of images in our data set, and the fake is generated image from generator. So discriminator tries to discriminate between images from our data set and the images from generator. That is role of discriminator. And simply binary classification, just binary classification. And this is one of the discriminators that people used at the time, patch GAN. Instead of just simply providing, averaging entire image into a single vector, it estimates, it outputs classification score for each patch from image. But basically, the strategist just takes an image and they classify whether it is real. Real means images from our data set. Fake means images from generator. And then, as I introduced, these two modules are primary modules in GAN, and they are fighting each other. They have different objective function, actually opposite objective functions. So in training, the GAN plays a two-player minimax game. Two-player means generative and discriminator. The generator tries to create realistic images to fool the discriminator into thinking they are real. And the discriminator tries to identify the real images from the fake. So that these are opposite, right? Generator tries to create good images that can fool discriminator. And then discriminator tries to identify whether the input image belongs to real image when our data set or generate images. So they have opposite objective functions, and that is the reason why we call adversarial network in its name. Generative means, still it is interested in data distribution, not labeled space. And the adversarial means generator and discriminator are trained adversarial way. They are fighting each other during the training and neural network. So let's start with the just random noise, as I introduced. There's random noise, and generator outputs some image. And the discriminator takes image and then outputs just a probability whether this image belongs to real or fake, right? So this shows the entire pipeline. So from randomly sampled noise, generator takes the randomly sampled noise and then outputs some image. And the discriminator, these are parameter of neural network. G is parameterized with theta. Discriminator is parameterized by phi. And the generator takes a randomly sampled noise and then outputs some image, so generate some image. And then discriminator takes fake image from generator or real image from our data set. Of course, these parameters are shared because discriminator, we only have one discriminator. And then it just simply do a binary classification, whether the input image belongs to real or fake. And there are two loss functions. Loss function for generator, loss function for discriminator. Loss function for generator. This slide shows loss function for generator. As I said, the role of generator is to create realistic images so that it can fool discriminator. Fool discriminator means originally, discriminator actually, it needs to classify the fake image into 0. So here, 1 is real and 0 is fake. Discriminator actually, it should classify the fake image into 0 class. That is the primary role of discriminator, right? But when training generator, not training discriminator, when training generator, we want discriminator to classify the input image belongs to real image class, right? So when training generator, we minimize this loss function. This is from binary cross entropy. Y log y hat. Y means ground truth, and y hat also binary. Y is ground truth, and y hat is estimated one. It's a binary cross entropy, right? Binary cross entropy. And there should be minus 1 divided by n. So that we want this output of the generator to be classified in the class of 1, so that then y is 1, and then we have, from BC we can derive this one. This term disappear, and then we only have minus log y hat, right? When training generator, we want generator produce images which can fool discriminator, and then fooling discriminator means discriminator classify the generator's image, generator's output, classified to real image class 1. 1 is real, right? So when training generator, the goal is loss function is this one. You need to be aware of this minus sign, minus log y hat, where y hat is estimated image. X is random. X is this one fake image, and the d phi is a discriminator. So we can pass. We can pass X as input of d phi. Then we can. Y hat is a d phi X, right? So that this is loss function for generator. Discriminator, opposite. When training discriminator, we want generated image belongs to fake class, and then our images from real training set belongs to real class. So let's recap the BC, y log y hat n log. Okay. So this is binary cross entropy, and then when training discriminator, as I introduced, we want discriminator to classify the generated image belongs to fake class, 0 class, and then real image from a data set. Let's say we have data set. Image from real data set belongs to real class, 1 class. And then we can simply, just use those numbers. So when, for fake images, we want this one has 0 label, so that this one disappear, and then we can simply log 1 minus y hat minus, right? That is the first loss function for images from generator. If G theta z is a generated images, right? We have z, and the G theta z is a x, that is generated image. When generated images becomes input of discriminator, then we want such images belongs to 0 class, right? We can just use such numbers into BC equation. So that the first loss function for images from generator becomes minus log 1 minus d phi G theta z. That is the first loss function for images from generator. And the second loss function, images from our data set. Let's say we have a data set, a set of real images. We pass such images to discriminator, and then in this time, we want such images belongs to real class, right? This class. And then we can simply plug into this equation. Y becomes 1, right? Then this one disappear, so that minus log y hat, right? Minus log y hat. Y hat is output of discriminator, this one. D phi x dash, right? Where x dash is from our training set. right? So there are two loss functions. This is simply binary cross entropy for discriminator. Images from generator, it belongs to fake image class, and then images from our data set, it should belongs to real image class. It's a binary cross entropy. But the important thing is that when fake images pass to a discriminator, the objective function is opposite. When training generator, we want such image belongs to real class. But when training discriminator, we want such fake image belongs to zero class. So that, as I introduced, there's an adversarial training. Generator tries to make fake image, its output belongs to real class, right? Real class when training generator. While when training discriminator, we want such images, fake images belongs to fake class. So they have opposite loss function, opposite objective function. That is adversarial training in GAN. So in summary, there is a minimax game between D and G. So we're used to just minimizing loss function, but let's first see maximizing loss function and minimizing loss function. Let's first see this one. So here, phi is discriminative, right? Discriminator, generator. So that we want to maximize this one. So maximize this one means we want images from generator belongs to zero class, and then we want images from data set belongs to real image class. But usually in practice, instead of maximizing loss function, all this kind of machine learning frameworks are, implementation, all the things we are used to minimizing loss function. So we change, instead of maximizing this loss function, we simply change the simple math trick, and then we minimize this one. This one are the same as the previous slide, this one, right? The first loss function for generator, minus log 1 minus d theta, d phi, g theta, z, right? This one. And then the second loss function is minus log d phi x dash. This one, right? So instead of maximizing this one, in practice, in real-world implementation, we minimize this one. But mathematically, they are the same. If you're interested in binary cross entropy, then not perfectly the same, but more or less the same. There's no problem, just maximizing this one into minimizing this one. So in practice, people simply minimize summation of these two loss functions. When generator's output becomes input of discriminator, we want such image belongs to zero class, and then if images from data set becomes the input of discriminator, then when we make output of discriminator be the real image class. That is about this one. And the here generator training, as I introduced, instead of doing this, people often minimize this one. Minus log. Here they say there is no minus, right? There is no minus. But, in practice, people often just simply do this one, minus log d phi x. This is directly from binary cross entropy. But mathematically, they are more or less the same. Without minus sign, 1 minus d phi g theta z, minimizing this one, is more or less equivalent to minimizing minus log d phi x, more or less similar. So in practice, people just simply minimize this one. Because we can directly use binary cross entropy loss function without some custom implementation. So that your discriminator, the generator tries to minimize likelihood of generated image being classified as fake, right? Minimize likelihood of generated image being classified fake. That means tries to maximize likelihood of each generative image being classified as real, right? According to a fixed discriminator. So that is the reason why we have minimax game, adversarial training, opposite objective functions, all the things are from this one. They have opposite directions. When generated image becomes the input of discriminator, the objective function could be very different. So in training, GAN plays two-player minimax. Generator tries to create realistic images to fool discriminator into thinking they are real, and the discriminator tries to identify the real images from the fake. So that is minimax adversarial training in GAN. And this one shows, and then this one. This one we already covered this one, and then so what actually it's a little bit implementation detail. When I mean in the previous slide there is a two loss functions for generator and discriminator, but if we do that jointly, then something bad can happen because the training becomes quite unstable. But that the in practice, people train generator and discriminator alternatively. In first step, they fix the generator and only train discriminator. And then for next step, people freeze discriminator and only train generator. And this one shows the pseudocode of training GAN. This one shows the alternative training between discriminator and generator. Let's say training data consists of a collection of unlabeled images. And then you can skip some detail, but here, the first for loop is here. Sample, image, noise, some details, and then the important thing is that for k steps, update discriminator by ascending stochastic gradient. Ascending means maximizing this loss function, but we can change, we can use mathematical equivalent form with the minimizing loss function introduced in previous slide. But here, we first update discriminator while generator is fixed. Generator is fixed so that this gradient does not affect generator. This gradient from this loss function only affect discriminator. So here, G is fixed. And then, so after training, so K is, of course, maybe larger than 1, so that people use multiple iterations to train discriminator, and only one iteration. There is no for loop, right? D is fixed. And then we can sample and noise sample from noise prior normal Gaussian distribution, and then we can update generator by descending the stochastic gradient. Here, D is fixed. So gradient is backpropagate from here, right? Gradient is backpropagate from here, right? Here, and then go to backpropagate to generator. But this gradient does not affect discriminator. Discriminator weight does not fix. Here, when training generator, for generator's turn, discriminator is fixed, and this gradient does not affect discriminator. But that makes sense because we want discriminator to classify this fake image belongs to 0 class. But if we apply this gradient to discriminator, then discriminator has two different opposite gradient, right? That doesn't make sense. So when training generator, we fix discriminator, and then this gradient only affect generator without affecting discriminator. That is happening in here. D is fixed, and we only update generator by this gradient stochastic descent. And so there is a k step means k is of course larger than 1. So there is we need very careful trade-off between discriminator and generator. If we set k too high, then discriminator is trained multiple iterations, many iterations. The generator is trained only few iterations. Then balance between discriminator and generator becomes mess, right? So we need very careful, make a very careful balance between discriminator and generator. If k is too small, then discriminator is too weak, right? Because discriminator does not have enough training iteration. G is too strong, so that G is too strong means it can easily fool discriminator, then we cannot achieve what we want. So, on the other hand, if k is too large and the discriminator becomes too strong, the generator fails to fool discriminator so that we cannot reach our desired quality bar. So that there should be very careful balance between discriminator and generator. Changing this k step is one way to make a balance between discriminator and generator. There are actually many heuristic training tricks to make this kind of good balance between discriminator and generator. And that is the reason why training is quite unstable. There are many hyperparameters, and system is not very robust, actually a little bit fragile. So it is very difficult to make a good balance between discriminator and generator. And this one shows one of the representative work in GAN research, style GAN introduced in CPR 2019 from NVIDIA. This is traditional GAN, right? We learned this kind of system, right? From randomly sampled vector, we just do some convolution, fractional Strider convolution, and then just upsample images. Style GAN is style-based generator. From randomly sample, it extracts style information from latent Z, and then additional noise is here. Is a constant, and then when generating image, it uses this kind of latent information as a style information to change style of input image. So that you can see here from B and source A, source B, you can see that images from this woman remained almost the same, while only style changes. I mean, the skin color or hair color just changes, while your facial appearance remains almost the same, so that we can make a image editing naturally with this style GAN, just using a style transfer technique, so that we can use content of image from the source image B, while you can use style information from this image, so that we can make the facial appearance almost the same, while we can simply change style of this woman, right? That is style GAN. And this shows the qualitative result of GAN. You remember the result of VAE? It was quite blurry, right? Compared to VAE, when trained with good hyperparameter and good balance between generator and discriminator, GAN gives good result. Facial image becomes much sharp and much more detailed than VAE's outputs, right? But as I said, training GAN is very unstable, very difficult actually. There are many hyperparameters because we need to make a balance between discriminator and generator. One of typical failure cases is mode collapse. As I introduced, when training GAN, while we provide the mode is just a binary, real or fake. I mean, imagine you are generator. Imagine you are generator and your teacher is just giving good or bad without any detailed guidance. Then that is the generator, right? So, I mean, for generator, it is very the supervision signal is too less informative, so that one typical failure case of GAN is that simply generate few images well to full discriminator. I mean, generator, this is mode class. As you can see, image looks almost the same, right? This image looks almost the same, looks almost the same, looks almost the same. Generator can produce few images well without generating diverse images. That also minimizes loss function, right? It can still full discriminator, but there's no diversity encouraging loss term. I mean, mode is this one. Mode is this one. When we have a Gaussian distribution, the mean is called mode. And mode class means mode is destroyed. So that is the reason why this mode collapse happens. We have too less information. VAE, we have reconstruction loss, we have explicit target, very detailed guidance, very good gradient. But when training GAN, we have only binary supervision that is too less informative, so that even generator can produce this kind of few images well, only few images well, without generating diverse images. It can still fool discriminator. Then in terms of training objective function, there's no problem, right? But this is not what we want, so that this kind of mode class happens quite often when training GAN. But the VAE and diffusion, they have reconstruction loss instead of binary loss, right? Reconstruction loss is an explicit target, so it is very informative. So VAE and diffusion, mode collapse does not happen much, but when training GAN, we can see lots of mode collapse without careful making balance between generator and discriminator. Anything is unclear about the GAN? Any question about GAN? No problem. And diffusion model is used in everywhere these days, right? So the intuition is so that we pick a noise distribution here we also use normal Gaussian distribution. Normal Gaussian distribution, and consider data x corrected under varying noise level t to a given noise data xt. Here is some xt is somewhere around here, and this is x. Xt equals 0, x0, and x1, xt. Train a neural network to remove a little bit of noise, right? So taking this noise image as input and t as input as well, and then it tries to go denoise the noise image to denoised one, right? That is the role of neural network in here. We will see detail later. And inference time, so that there is some clean image and noise image. Noise means normal Gaussian distribution. The reason why we make clean image to noise image is that we want to use normal Gaussian distribution. Normal Gaussian distribution, we know all of the normal things in normal Gaussian distribution. We can randomly sample something from normal Gaussian distribution, so that we want to transform the clean images to some representation that we are familiar with. Images, it has too complicated distribution. We cannot know exact distribution of real images, but if we can define some latent distribution, latent space with normal Gaussian distribution, we know everything, right? So that is the reason why we inject noise to make into normal Gaussian distribution. And inference time, we sample x1. X1 is here, right? We sample from normal Gaussian distribution and apply f theta here, neural network, which can denoise, progressively denoise the randomly sampled noise here, x1 to x0. So progressively denoise to x0. It's a little bit different from VA and GAN, right? The major difference is that we have applied f theta many times. That is difference. VAE, GAN, we use decoder or generator only once, right? There's no many times. There's no iterative generator. There's no iterative decoding. But here, diffusion, the neural network is trained to remove noise, a little bit of noise, not entire noise, just a little bit of noise. And then in inference time, we apply f theta many times instead of only once. That is difference between from VAE, GAN, and diffusion models. VAE, GAN, we use decoder and generator only once, but diffusion model, it use neural network multiple times, which makes quite slow here, slow generation. Good quality because of iterative decoding, I guess. I mean, instead of doing single feed forward pass, instead of just simply single feed forward to decoder and generator, we have denoising network, which works in iterative manner. And then training is stable than GAN. There's no adversarial such stuff. There's no fighting each other in the training stage. So the training is stable. And also we have reconstruction loss. So that makes training quite stable. But as I introduced, slow generation. The reason is that we apply f theta many times. Instead of denoise GAN and diffusion, it goes directly to this one, right? Instead of iterative progressive denoising, VAE and GAN directly go to x0 from x1, right? But diffusion network, it progressively denoises the sample. That is the reason of good quality, at the same time, slow generation. This figure shows the stable diffusion. And the right one, I guess some of you are familiar with Nano Banana from Google. This image is generative one. This image is quite expressive and very good quality, I guess. And there are many algorithms in diffusion models these days, but let me introduce very basic stuff in diffusion model, rectified flow. So suppose we have a simple P noise, of course normal Gaussian, and sample from P data. So this is normal Gaussian. And then P data we do not know. We cannot know this one. So that this is a real image, and then the P noise are just a set of noise. And then on training iteration, we sample Z from P noise. We have normal Gaussian distribution, so that we can just randomly sample Z from normal Gaussian distribution. And then we have lots of training data, right? We have imagine we have many data. that we can just randomly sample some image. And T is uniformly sampled in a range of 0 to 1. And then we can define xt as a linear interpolation between x and z. So x is, as I introduced, this is real image, and z is a noise from normal Gaussian distribution, and the t is uniformly sampled one, and the xt is a purple one. It is defined as a linear interpolation between x and z. Here you can see xt is a linear interpolation between x and z, depending on the value of t. And v is the vector from x to z. And then training is this one. Train a neural network to predict v. Neural network takes xt and t, and it is trained to output v vector. That's all. Quite simple, right? The capability of diffusion model is very good, but training objective function is quite simple. Just take a linearly interpolated xt, and then t as the input, and output v. That's all. It's too simple, right? And actually, the core training loop is just a few lines of code for x in data set. We have data set and we sample x image. Z is randomly sampled, random sampled from normal Gaussian distribution. Rand is a random and is normal Gaussian distribution. T is a uniformly sampled from 0 to 1. And then we define xt as a just a linear interpolation between x and z, right? And then model is a neural network which takes xt and t and outputs v, and then v is output, and then z minus x is the ground truth of the model, so that we can just simply calculate loss function between ground truth and estimated one. That's all. And after training, what we want is generating new sample, right? How can we sample? We start with the, likewise VAE and GAN, we always start with the randomly sampled normal Gaussian distribution. And then this t is a hyperparameter. We often set t is equals to 50. That is the number of iteration in the sampling stage. As I said, we do iterative sampling, right? We have hyperparameter. And then for t in this range, 1 to 0, where there are many intermediate values, we evaluate vt. Vt is this one. For let's say we have start with the x1. x1 is pure noise from normal Gaussian distribution. And then from x1 and t is 1. Neural network outputs some vector, right? Some vector. Vector between the noise and the data. And then we update. We start with the x1, which is a pure noise, and then we do progressive denoise by applying this estimated vt a little bit by dividing it with the t. Then x1 becomes to x2 divided by 3, this one, by applying this vector a little bit, right? And then we do the same thing again, we do this again. Then we start with the x2 divided by 3, and then we passed x2 divided by 3 and t to the neural network, and then it outputs vt. Then vt might be a little bit different, right? Because input changed. Here input was x1. Here input was x1 and 1. Here input is x2 divided by 3 and 2 divided by 3. So input is different, vector is different, right? Then we have different vector, and then we do a little bit of update here, and then so we now are here, and then now input change it, x1 divided by 3, 1 divided by 3. Then vector also changes, right? Vector changes. And then we simply update a little bit, right? So that finally reached to x0. X0 is clean image. After denoising, we have clean image. By doing this kind of iterative, progressive denoising, we got sampled image. Return x0. So here, the iterative sampling, progressive sampling happens in here. We set hyperparameter t, often set to 50, and then we include the estimated vector a little bit by progressive manner. And sampling here, sample is, as I introduced, just x0, this sample is x0, start with x0, just randomly sample one from normal Gaussian distribution, random normal Gaussian distribution. And then t here, 1 to 0, where there are a number of steps here. And the model takes sample and t, which outputs v, and then sample is iteratively updated by including this estimated v divided by num steps, right? We keep repeat this, and then at the end of this for loop, we return sample. That becomes the output of sampling. So training, sampling, training is, we have data set, we have a random noise, and the t is uniform sampled, and then we make a linear interpolation between x and z, and then model takes linearly interpolated one, and then t outputs vector, and then we train your network to predict the vector between noise and data. We keep doing this. The sampling, we have random normal Gaussian distribution, and then we iteratively denoise within hyperparameter num steps, which is often set to 50. We pass sample and t to model, and then we got v, right? We got v, and then we include the estimated vector a little bit by dividing it into num steps, and then we can keep repeat this to get final image x0, right? It's not very difficult, right? Despite this very simplicity, it works quite well. And sometimes, actually many times, we want to do conditional sampling, right? Here, there was no condition, just start with the pure noise. There was no condition, but in many times, actually, we want some conditional sampling, conditional diffusion model. There are many ways to give conditional information to diffusion models, but one way is classifier-free guidance. So here, y is a condition. From the, let's say x is just to start with the, here x is a real image, z is the random noise, y can be like a text prompt. Sometimes we can just randomly sample any arbitrary images, right? Maybe we can do that, but in many cases we want to give some condition information like a text prompt or some rough visualization of images or some pose of human or geometry of some scene or object. We can do some kind of giving them as a condition, and then generate images based on the condition. So that y is a condition at that time. Text prompt or geometry, anything. And the model takes y as well, and y user's input and y. How can we do this? That is, here we have classifier-free guidance. So there's a small change in training. With some probability, like 0. With a half probability, we set y to y equals to null. Y null means just empty condition, right? We give with some probability we set condition as a 0, but that means there's no condition actually. So during the training, the entire training is almost the same, but the difference is that with some probability with the threshold, we train it as if it is unconditional generative model. Y with some probability becomes 0, so that in some iteration, it is trained as if it is unconditional generative model, right? Randomly drop y during training. So when y is set to null, then the same model is used for conditional and unconditional training. Conditional, unconditional generative models. And then we have a same model is conditional, conditional concern, noise xt. And then xt is somewhere here, right? We have xt. And then we pass y, this one, no space. This means just a y null. For example, text prompt, we just pass this one, just with quotation mark, just empty string, just a white space, no text. That means y no for the text prompt. So we have xt here, somewhere between noise and data space, and then we y no means just quotation mark without any text. For example, t is just t. That means we know, right? There's a vector, but from no condition. And then we have vy at the same time, where y is used. We have a conditional signal, right? And then we have y. It points toward. So that here, when empty condition is used, the vector points toward px, without any. That is prior distribution, right? Prior. This is posterior. Prior distribution in Bayesian rule, without any observation, without any condition. When y is set to y no, then the vector points towards prior distribution, and when y is used, then it points toward posterior. So we have two vectors, right? We have two vectors. And CFG is from classifier-free guidance, CFG. CFG is just a some linear weighting between Vy and V null space. So what does this mean? Let's say W is equals to 0.5. Then 1.5 Vy minus 0.5 V null. That means we give strong focus on Vy while we remove some part of V null, right? That means we are strongly focusing on Vy. So here, Vy, V null, VCFG, as you can see, VCFG is more biased to Vy by removing V null, and then we add the same amount of Vy, right? This one. The VCFG, it includes the condition was stronger than Vy, because we get rid of V null, and then we add the same amount of conditional information to the Vy, right? So that is classifier-free guidance. By calculating two kinds of vectors from unconditional generation and conditional generation, we make a weight balance between Vi and V null, where W is positive. Then it points towards Px y, where it points more towards Px y than this one. That is the one way to give a conditional signal to diffusion model. Actually, this kind of and classifier-free means earlier method. Literally, it used classifier. They use a discriminative model like a classifier to compute direction, but these days people do not use classifier, so that is the reason why we call this classifier-free guidance. We give guidance. We give guidance by sampling two vectors, right? Vy and V0. But it is classifier-free. There is no classifier. There is no additional classifier. That is the reason why we call this classifier-free guidance. In the training, with some random probability, we drop y so that we train as if it is unconditional generation. And then sampling, we sample two vectors from y and y null. We have Vy and V0. We make a linear weighting between Vy and V0. We reduce the impact of V0. We increase the impact of Vy so that we can make a guidance during the denoising iteration. We can make a guidance where the denoising trajectory tries to more focus on conditional information. That is the CFG, conditional-free guidance. Used in every year in practice, very important for high-quality outputs, used in literally everywhere. For example, if you want to generate the images with text prompt, then we can set y no as the empty string, so that we can, inside of model, it outputs two kinds of vectors, and then in outputs, we have a weight balance between Vy and V0 to get good quality of outputs. If W is equals to 0, then it is the same as the Vy, right? W equals to 0, VCFG equals to Vy, right? but if W is equal to maybe 100, maybe we can set very high W, right? Of course, in such case, we have some bad result. The model is, the model is very strongly biased to condition, so that, but it loses some V null. So V null means it is, just prior distribution of image, right? It models some prior distribution of image. It has low probability for images with arbitrary patterns. Images with some arbitrary images, it has low probability. So if we get rid of V null too much, then it loses realism of image, it loses plausibility of images, so that if W is too high, then something bad happens. W is equals to 0, then it produces some result, but it does not exactly follow the condition. So we need to make a balance between Vy and V null. And then this is sampling. And it's very important to understand how the value of W affects the quality of output. When W equals to 0, then V is equals to Vy, right? Then what does this mean? If W equals to 0, then V equals to Vy, then condition is not strictly included in the generation pipeline. It is included, but maybe let's say we get text from like give me images of red apple, but give me some images of orange color apple. Then without CFG, if W equals to 0, then maybe generated image looks like just a red apple instead of orange color apple. It produces some plausible image, but it does not strongly follow the condition information that I provided to the model. If W is equals to 100, then what does happen? Let's say I gave a text prompt like give me orange colored apple. Then maybe very strong orange color apple. I can't draw. It looks like apple, but the color is very strongly orange color, so it does not look like apple. So during the generation, it tries to include condition as much as possible because we provide very high W, so that if I gave me orange colored apple, then it provides some orange color something, but it does not look like orange colored. It does not look like apple. Maybe orange colored some circle, orange colored sphere, but it does not look like real images. So we need to make a balance between Vy and V0. If W is too low, then impact of Vy is too low, so that the generation cannot include the condition as much as possible. If W is too high, then the generated image might not look like real images. The plausibility of image decreases, so that we need to make a balance between Vy and V0. Let's quickly do this. Latent diffusion model is like so we actually start with the image and add noise to the image, but in practice, actually people use encoder and decoder. We use encoder, and then we encode image into some latent feature, and then we decode latent feature to image. But where encoder and decoder comes from? Actually, that is, where is it? Okay, that is actually VAE. People use VAE to pre-train VAE. People pre-train VAE, and then they encode image into latent space, and then do diffusion steps in the latent space only. Here. So train diffusion model to remove noise from latent encoder. Encoder is frozen. So after training, we sample random latent, and then we have a this kind of denoising network inside of latent space, not image space. We are interested in this purple color latent space. We encode image to some latent feature, And then we do this kind of all these steps like a denoising, CFG, all the stuff in the latent space. And then after denoising, we pass it to decoder to get image. So instead of doing this kind of diffusion steps directly on image space, people use encoder and pre-train encoder and decoder, and then do this kind of diffusion steps in the latent space instead of image space. That is called latent diffusion model, LDM. We do this kind of diffusion stuff on the latent space, where latent space is typically from pre-trained VAE. Here, we use VAE's pre-trained encoder decoder to define latent space, and then we do this kind of diffusion steps on the latent space. But as we note, decoder output, VAE's decoder output of blurry results, so that when pre-training decoder, we get a discriminator, right? There's a combination of VAE and GAN, right? When training VAE, we typical VAE train only with encoder and decoder with reconstruction and K divergence loss, but decoder's output is blurry, so to get sharp images from decoder, we add discriminator when training VAE. So it's a combination of VAE and GAN. We have a discriminator here. So it's like use all the pipeline, VAE, GAN, diffusion, all those things. Encoder and decoder are VAE, this discriminator from GAN, and this denoising is from diffusion, right? So it uses all the things in latent diffusion model. When pre-training, for the pre-training, training encoder decoder discriminator that is trained before training denoising network, and then after training this, we got this, and then we use this for denoising network training. So we use all the things, VAE, GAN, diffusion. So this is our summary, VAE, GAN, diffusion. VAE, encoder and decoder, reconstruction loss and K divergence loss, stable training, fast sampling, but blurry output. GAN, generator, which is more or less similar to decoder of VAE, and discriminator. Binary supervision, real or fake, often unstable training, which result in both collapse and fast sampling, a sharp image. Diffusion, denoiser, that's more or less similar to decoder of VAE. Reconstruction loss, there's only one loss function, right? Reconstruction loss. Stable training, but slow sample because there's iterative denoising. And sharp outputs. And next time, we'll study how diffusion models can be used for 3D computer vision graphics. Before diffusion models, the most typical way to get images is using rendering equation with 3D geometry, texture, camera, light. But diffusion model can generate images, videos without them. This is actually a very interesting point. Now people can no longer rely on 3D geometry, texture, camera, light. People can just simply use text prompt or some simple image to get new images or videos. Maybe so that we can call this a new rendering engine. And there's actually pros and cons compared to approaches with rendering equations. So we will study this kind of relationship between diffusion models and non-generative models from next time. Anything you want to have discussed? Let's check the attendance and finish.